Welcome everybody, and today we will be talking about EEG or QEEG. So welcome to QEEG. My name is Dr. Halter, and I will be your presenter for this presentation or this webinar. So I'll talk to you about this whole process as if you did not know what EEG or QEEG stood for and what it is. So let's get started. So what is EEG? EEG is electroencephalography, and it's a non-invasive technique that provides us a measure of the electrical activity at the surface of the scalp. So the way that this differs from other imaging techniques such as MRI or CT scan or other imaging techniques is that a lot of these other imaging techniques look at the structural integrity of the brain. So if there's a lesion or if there is some type of tumor or some kind of structural abnormality in the brain, that's what those imaging techniques are good for. But different from those, EEG or electroencephalography is a measure of the functional integrity of the brain. So we can see if different areas of the brain are functioning the way they're supposed to. So that is the purpose of using EEG. And it allows researchers and psychologists and other individuals who use this technology to look at the underlying mechanisms that are part of the perception process and that lead to our behavior. So again, we have a signature in the brain of any type of emotional experience or behavioral experience that a person may be experiencing. So to begin with, before we start anything else, we have to understand where we get this information from. So the first step is to look at the placement of the electrodes, and commonly a system that is used is the standardized 1020 system. So those are 19 different locations on the brain, and each of those is labeled with a letter and a number. So the letters tell us if it's in the front or frontal pole, that is FP. Then F is frontal, C stands for central, T for temporal, P for parietal, O for occipital. Then even numbers are on the right and odd numbers on the left. And then the midline channels are, again, they have a Z after the letter. So FC would be front central, ZZ would be the vertex or the center, and PZ would be the parietal center or midline. So now that we understand that those are the placements of the electrodes where we collect the electrical activity from, we have to somehow understand where or what we are looking at. So in order for us to really interpret the electrical signal without having all the noise that's in the environment, we have to use different arrangements of electrodes. So whatever is similar in any of the electrodes that we use, that information is pretty much discarded, and the difference in the channels is what is amplified. So that is what the differential amplifier does for us. So we have various different types of montages. We have mainly two categories, one of which is bipolar, the other one is referential. So the bipolar montage looks at all the electrodes in a chain, and it connects the voltage of one electrode to an adjacent electrode. And then that electrode then becomes the active, and the following electrode becomes the reference. For instance, if we look at FP1 and F7, that is the first pair. So FP1 would be the reference, F7 would be the active electrode. Then the next pair along that chain, we have F7 and T3. So F7 now becomes the reference electrode, and T3 becomes the active electrode. So the way that this works is to localize certain types of activity. If we look at the picture here to the left, we have FP2, F8, T4, T6, and O2. And as you can see, the closer that we get to any kind of activity, for instance, this activity that is where it says -50 microvolts, let's say we want to know which channel is the closest to that activity. The way we can tell that is because if we look at the EEG or the raw data or the squiggly lines, we will see a deflection downward at FP2 and F8. Then that deflection becomes bigger as we get closer to the electrode that is closest to that activity. And then once we pass that activity, the deflection is in the opposite direction, and that is what we call a phase reversal. And that is one of the reasons why bipolar montages are excellent in trying to determine where an activity is or which channel certain activity is prominent in. So we have in this montage right here, it's called we call it the longitudinal bipolar because it's from front to back. So since it looks like two bananas when we look at the temporal chain and the parasagittal chains, it looks like two little bananas. So another name for this montage is a double banana. So that is one type of montage, the bipolar montage. So when we have this bipolar montage, one of the issues we have is the end of the chain phenomenon. Because as you can see, if we looked at activity that is in the front now, since FP1 does not have any channel it's compared to, we don't see this phase reversal. So how do we deal with that problem? We can look at another montage that is a bipolar montage. And this montage would be the circular bipolar montage. Or we can also, as I mentioned earlier, look at a transverse bipolar montage, which looks at from one side to the other, from the left to the right, instead of from the front to back. So again, that's a way we can look at different montages and then understand where exactly certain activity is happening. And that's why it's usually very common for people to look at more than one montage when they analyze the EEG. Because that way you get more information, because certain montages have strengths and weaknesses, and every montage has strengths and weaknesses. So that is, again, the bipolar montage. So then the second type of montage is the referential montage. In the referential montage, we have all of the channels averaged out, the activity of all the channels, and compared to each channel. And again, whatever is different from the average is then becomes visible on the screen as the activity that's in that channel. However, those references that we have at that point become the only reference for all the channels. So we have the average reference montage, and then we have the Laplacian montage, which is a little bit like the average reference montage, but it only looks at the channels immediately around, as in this example, around F4, and then compares that to F4. And whatever is different at F4 from the average of the other ones is then shown as the activity in that channel on the screen. So why does that help us? It helps us because it does away with certain types of effects that are just at one location. So we see more what's happening throughout the entire scalp or across the entire brain. So, all the channels that are on the scalp. So these virtual channels, because again, the average reference or the Laplacian reference, although the references are virtual, they're not an actual reference. There's also the linked ear reference montage, which uses the linked ears, either one or both of the ears and the average of the ears, and compares it to the rest of the channels on the surface, and whatever is similar in the ears compared to the rest of the channels is ignored, and the differences are amplified. The only problem with the linked ear montage is that it is assumed that it is an empty channel or is electrically silent. And we know that that is not the case because we can see and collect a pulse from the ears. And so there is this potential to have a cross-channel contamination if we use the ears as a reference. But just for information for this webinar, it is important to keep in mind that when looking at montages, the best way to go about it is to look at a reference montage, or like the average reference montage or the Laplacian montage first. I personally like looking at the average reference montage first, then I go to the Laplacian, and then I go to a bipolar montage. And the reason I do that is because it's like looking at something like, let's say we're looking at a map, or we're trying to locate a house. And so we have the 30,000-foot view of an airplane, and that is like the average reference montage. It gives me a general idea of the electrical activity across the scalp. Then if I want to get a 10,000-foot view, I can look at the Laplacian montage and get a little better localization. And then from there, I can then go to the bipolar montage to further localize the activity. And then once I'm at, let's say, now I'm at the house, looking at the house from a 30,000-foot view to a 10,000-foot view, then the bipolar would be, I'm looking at the house. And then we go into then we can go to the Loretta images, and we're going to talk about those here in a second. And that lets us localize the source or the estimated source of where the activity is actually coming from. So that would be like looking inside the house. So that is my analogy for the different montages. So now that we know montages, and we know that we have to put electrodes on the surface of the scalp to get at certain locations to get electrical activity, we now have to understand something about the terminology that we use in EEG. And with that in mind, we first have to understand what the different frequencies mean and what they're associated with. For example, we have the infralow frequency, which is less than 0.5 hertz. And again, that is more the attitude of the brain. It lets us know if a brain is in a certain state, a certain overall state. And then when we look at slow cortical potentials, which is around 0.5 hertz, we can see if the brain is ready or not to engage in the next activity. So the very, very slow waves are more the attitude of the brain. Then we get to the delta activity, and that is commonly known as 0.5 hertz to about 3 or 4 hertz. And that activity is usually seen mainly in the deep stages of sleep and meditation. However, we should not see delta activity in the wake brain. So again, this is the type of activity we see in a deep sleep. And again, it's important in deep sleep because that allows the pituitary gland to release certain hormones like growth hormone, and that helps the body recover. So that's why it's so important for us to be in deep sleep for a certain amount of time during our sleep cycles. Then we look at theta activity, which is usually another low frequency activity, 3 to 8 hertz. And again, we see that usually right when somebody goes to sleep, when somebody's daydreaming or meditating. So from there, we then go to the alpha frequency, which is around 8 to 12 hertz. And that is usually when somebody is alert and awake, but not really processing anything mentally or cognitively. Then we get to beta frequencies, which is 12 to around 38 hertz. And this is usually when somebody's performing some kind of mental work. And again, it's seen predominantly in the frontal cortex. And also the source of this activity is mainly created by the cortex and the brainstem. Then we get to the gamma frequencies, which are 38 hertz or above. Some people would say 35 hertz and higher. And this is the fastest brainwave activity, and it usually occurs when we see sudden changes. And it's also visible in elite performance, as well as consistently visible in individuals that have some kind of psychotic episodes or yes. So again, these different frequencies, they should be in the brain at within a certain range. So there's not like, okay, I want to have a lot of this activity, so this because it's a better frequency. That is not the way to look at EEG frequencies. We have to look at them as, okay, there should be a certain amount in certain places at a certain time. the typical amplitude of the brain waves are somewhere between 10 to 100 microvolts. And that is what is considered the normal, with quotation marks, EEG. So now that we understand some of the terminology of the different frequencies and brain waves, we now have to understand how to read the background EEG. It is so important, and this is one of the key areas that a lot of people overlook, unfortunately, but it is one of the most important factors in knowing, really understanding what the brain waves are telling you. The first part, or the first aspect of background EEG that I want to talk about, is organization, and looking at specifically at continuity. The organization of the brain is actually includes various different aspects. It includes continuity, symmetry, and the anterior-posterior gradient. And I'll go through those one at a time. Continuity, we want the waveforms to be uninterrupted by, flat activity or attenuated activity. And that's what we should see in healthy adults. We should see a continuous EEG. So if we look at the images here to the left, we see that the EEG is continuous throughout the record up here on top, with minor fluctuations, which are normal. Aside from the eye blink, of course, that we see here, but that is artifact. But other than the artifact, this sample up here is continuous. An example of discontinuous would be something like, and again, this is more of an example that is more obvious because, again, I'm trying to make a point here. So we have this burst activity, and then we have attenuation and suppression. Again, we should not see these types of bursts of activity in a healthy brain. Yes, we have certain times when certain areas are synchronized and when other areas aren't synchronized. But as long as those are, from second to second, there is a shift. That is what we should see in a normal brain, or a healthy brain, I should say. So from the continuity, we now go to symmetry. So this right here, these are bipolar montages. And the way you can tell is each location has an active and a reference electrode. So right here, we have FP1, F7, F7, T3, T3, T5, T5, O1. So again, we have the left side, then we have the right side on the front, then we have the left side of the center, and then the right side and the center, and then we have FZ and ZZ here on the bottom. So again, it is symmetrical because if we look at the left and the right side, which is easier to do with a bipolar montage because of the way that the channels are arranged, we can look at, for example, FP1, F7, and then FP2, F8, and we can compare those. Are those relatively similar? Yes. Then we look at F7, T3, and F8, T4. Do they look relatively similar? Yes, they do. And of course, we're just trying to get an understanding of what the background looks like. So this top record here is relatively symmetrical. And now when we look at asymmetry or an asymmetrical record, we can look at, again, the left and the right side. So when we look at, again, the same channels, FP1, F3, and then we look at FP2, F4, we see that there is different slow wave activity happening. And then also at FP1, F7, and then FP2, F8, if we look at those, we see drastically different activity. So that would be asymmetric because the left and the right side aren't the same. So that is symmetry. So that's still part of the organization of the background. There's also certain parts that are typical, or the typical amplitude asymmetries that we see across the brain. So we should see more beta activity in the left hemisphere, more alpha in the right. Also, more beta anteriorly and more alpha posteriorly. So if we see that, that is a normal, those are normal or typical asymmetries. So the last part of organization is the anterior-posterior gradient. So if we look at an EEG, we should see in the front, we should see higher frequency and lower amplitude. And as we go back, we should see a higher amplitude and lower frequency. And there's an inverse relationship commonly with the frequency and the amplitude. The higher the frequency, the lower the amplitude, and vice versa. So again, we should see this type of activity in the brain, especially when with the eyes closed record. We should see that even more prominently than with the eyes open record. And so the next thing we need to know is, what is the posterior dominant rhythm? Why do we care about the posterior dominant rhythm? Because it shows us how the thalamus, or the center part of the brain, communicates with the cortex. The thalamocortical pathways go from the center of the brain to the back of the brain and then towards the front. And that's why with eyes closed, when there is no stimulus in the occipital lobe, we should see, posteriorly, we should see this type of alpha activity that we see here. And again, you see the anterior-posterior gradient going from front to back on the left side here on top. And then right here, FP2, F4, we see the same kind of anterior-posterior gradient, which is exactly what we want to see. And then, of course, we want to see this posterior dominant rhythm. And this PDR, or posterior dominant rhythm, should be relatively continuous. However, there's a slight fluctuation in the frequency from one epoch to the next. And when I say epoch, I mean, for instance, one period of time, or in this case, to make it simple, from 1 second to the next. So if we call each second an epoch, we should, if we count the peaks, come up with the same number every time we go to the next epoch. However, that varies slightly from epoch, or can vary slightly in the healthy brain from epoch to epoch. However, it should not change drastically in frequency, because that means that the thalamus is not communicating with the cortex effectively. And we commonly see things like that in people who have certain conditions, such as hypervigilance or trauma, and then also in people who have had some kind of head trauma or encephalopathy or brain bleed or tumor. In those cases, we sometimes see that the posterior dominant rhythm on one side is drastically different than the other. Or if we look at the FFT spectrum, which is the fast Fourier transform, which we'll talk about in a second, we see more than one posterior dominant rhythm, or like a bimodal posterior dominant rhythm, if you will. Also understand that there are about approximately 5% of the normal population that do not have a posterior dominant rhythm at all. So keep that in mind. So not everything that we see in the EEG should be taken as indicating a pathology or not. Everybody's brain is slightly different. However, there are some general rules of thumb that we're going through in this webinar that we should be looking for when we look through the raw EEG, or the squiggly lines. The posterior dominant rhythm is also associated with intelligence and ability to process information. And one thing that I also want to mention is that the slower frequencies, such as delta, theta, and alpha, are considered carrier frequencies. And they usually carry the faster frequencies, such as beta and gamma. So we have something called cross-frequency coupling. So that means that the slow waves carry the information long distance through the slow wave activity carries that information from one area of the brain to another area of the brain. And again, if you think about the posterior dominant rhythm, the faster it is, the faster it can carry information from one area of the brain to the next. Also, the higher in amplitude, that tells you about the capacity of the wave to carry information. So the higher the amplitude, that also allows the person to process more information or move information from one area of the brain to the other. So that's why I always tell people, keep in mind that frequency is more how fast something occurs in the brain, and then amplitude tells you about the capacity, how much information is exchanged between different areas of the brain. So that is the posterior dominant rhythm. Then the next background aspect that I want to talk about is variability and reactivity. And here again is a drastic example of there's no reactivity or variability in the top EEG, which is isoelectric or no electrical activity at all. So in somebody who is in a coma, you may see something like that. Then in a normal brain, you see reactivity. For instance, if we look at P301, we see that there's alpha activity, theta activity, and then again, there's alpha activity, then it's a sort of theta, which tells me that the person may be somewhat drowsy. Again, seeing theta in the posterior areas, as well as the frontal areas, is an indication that somebody may be drowsy. But we're going to go through that here in a little bit. So that's variability. And reactivity, again, looks at shifts in frequency that are, as a result of external or internal stimulation. For instance, if somebody is sleepy, where we see lots of background theta, we're drowsy, and then we knock on our desk, and then we see that the person is we see faster activity, that would be reactivity. So again, a normal brain reacts to stimulation, and that's what we should be seeing in the EEG. So now that we've talked about the three parts of the background EEG, the last part is state of consciousness. What does that mean? So in an awake adult, the EEG is marked by lots of different frequencies, mainly alpha and beta activity during the wake period. But there should, as I said earlier, there should be very little to no delta activity in healthy background EEG. Then, of course, we have eye blinks, we have movement artifact, we have all these different types of activity in the background that may not be real EEG. But if we see things like we see right here, these are roving eye movements, which are commonly seen in people who are drowsy and about to fall asleep. So the eyes move back and forth very slowly. And again, that is an indication that somebody's drowsy. Also, here on the bottom image, we see that in stage 1 of sleep, there's a lot of theta and also some beta activity. So if we have posteriorly, if we see alpha, that turns to theta, and then then they drop out and it's beta activity, that person is probably in the first stage of sleep. Then if we see K-complex in the sleep spindles, we know that they're definitely asleep. But we shouldn't even get to that point if we do an analysis of the EEG, where we look at the eyes open and eyes closed at a resting state. Now that we've discussed a little bit about the EEG and the raw EEG, we'll discuss a little bit about the benefits of looking at EEG. So since EEG has one of the highest temporal acuity from any of the imaging techniques, we can use it for feedback, for neurofeedback specifically. So we can look at the activity in the brain and then feed back that information back to the individual on a screen, and then make it perceptible to the person's senses, and then they can actually, over time, their brain learns to function more effectively and more efficiently. So we're creating more efficient and more effective neuronal connections and networks. So that helps us to treat things like seizure disorders, anxiety disorders, attention issues, schizophrenia, mood disorders, Tourette's disorder, TBI, strokes, learning disabilities. And this is not an exhaustive list. Now, before we go on, I want to also make sure that you understand that we do not see disorders in the brain. We don't see diagnoses in the brain. What we do see in the brain are different symptoms or different activity that is consistent with certain symptoms, and we see those in various parts of the brain, and that then helps us to understand whether somebody has an attention issue or an anxiety issue or with a memory issue, recall issue, processing issue, whatever the issue may be. But we are looking at the efficiency of the neuronal efficiency, and then we adjust that in neurofeedback to match what our desired parameters or goals are for the individual. And of course, the individual's goals is what dictates everything. So we can't just use the EEG or not even the quantitative metrics that are derived from the EEG as a diagnostic. What we can do is we can look at this activity. So first, I recommend you look at the raw EEG. You understand what's going on. You understand how to read the background. And then from there, you're able to take out all the artifact of the background of that EEG. And from there, you'll be able to create hypotheses of what's going on based on the activity that you see. And from there, you can then go and look at the quantitative metrics that are derived from the EEG, which we're going to go to here in a second. And then we also match that to the person's endorsements or experience of certain of their environment or the condition, and we make adjustments based on those matches. So we don't just look at the EEG and try to fix the EEG. Why not? Because some of the behavior of the brain or some of the activity in the brain could be compensatory functions, or they could be functions, especially like in individuals who are elite performers, that set them apart from the average person or the norm, and therefore you don't want to mess with those. You want to link brain activity to whatever somebody's experiencing, and if that is something that they want to, mitigate, or like such as a symptom of some sort, then we can work on that. But it also works the other way. We can use the brain's activity and make it even more, or shape it a little bit more, so it's more like the activity of an elite performer. And again, the elite performers have higher neural efficiency, so we should see less activity in certain areas of the brain that are associated with that task that they're elite performers in, versus a novice, where we would see more activity in different parts of the brain, because that person's brain is not lateralized and specialized enough to be as efficient as an elite performer. But that's where practice comes in. So that is the benefits of EEG. Now let's talk about QEEG. So QEEG are the quantitative metrics that are derived of the raw data, the squiggly lines. So again, the way that this happened over history was that a researcher named Dubois Raymond realized that, look, there in neurons or nerve impulse, there are electrical signals that can be measured. So again, before this, we did not have the technology that we have today, and scientists determined that electrical signals occurred in the body. So that was the beginning of everything. Then in 1929, Hans Berger published an article where he described patterns of oscillating electrical activity that can be measured at the scalp. And then that electrical activity wasn't just electrical activity, but that it corresponded to behavior or human behaviors, and that was another huge step in the history of QEEG. Then in 1930s to 40s, EEG then became more popular in terms of psychiatric or neurological sciences. So individuals started to realize, hey, maybe we can use this data to help people with psychiatric conditions, or also to help people perform reach higher levels of performance and become more elite performers. And then in the 1960s and 70s, we were able to look at different montages of the EEG. Then we were also now able to average this activity out and do calculations and get quantitative data. And then in 1961 to 74, a group at UCLA led by Ross Aday pioneered the use of QEEG by being the first people to use digital computers in the analysis of the EEG. And that is where we now get the quantitative EEG, or quantitative electroencephalogram. So keep that in mind, that it came out of, okay, we see electrical activity, to now we can change this electrical activity to make it easier to interpret, and we can now create graphs, head maps, and so forth. So one of the biggest keys in this webinar that I want you to understand that EEG and QEEG are not the same thing. EEG is the squiggly lines, the signal that we pick up from the scalp that passes through a differential amplifier, and then we see it on the screen. Then QEEG are the metrics that are derived and put through different mathematical equations and statistical data, and that those then give us things like the head maps we see here on the side, which make it easier for a practitioner to read or to see what's going on. One huge caveat I have here is this: learn to read this, the EEG, because once you learn to read this, you can then form a hypothesis, and then you can compare your hypothesis to the quantitative data that the software spits out at you. Why is that important? Because sometimes these head maps are averaging at their averages of the data. So they do not tell you about the morphology of the wave. They do not tell you about certain transients. And with transients, I mean certain bursts or certain kind of activity that is, that is important to note. For instance, any kind of epileptiform activity that would be important to note, and then refer the individual to a neurologist. But again, you may not see that in the head maps or any of the other data. So it's really important to know how to read this EEG first. Again, the quantitative EEG, in general, what it helps us to understand, it helps us to take this data of all these waves and then put them into certain graphics to help us better understand the data that is in the EEG. But from my experience, I've trained myself to look at EEGs over and over again, and I keep on learning as I get more experience, and the more experience I get, the more I realize that there's even more to learn. But again, it's like reading in a new language. When you first start this process and you look at the squiggly lines, it's like first you have to learn how to read letters. Once you learn how to read letters, you can put them together into words. Once you're able to read words, you can read phrases and sentences, and then the whole EEG will make sense to you. You'll become a master at pattern recognition. So that is what the QEEG tells us. Also, the QEEG allows us to, like as I mentioned before, we get information. If we do a full EEG, then we get information from all 19 sites. But those are estimates of the activity that's going on in the brain. Even though it makes it easier to read head maps, they may or may not be able to tell you the whole story, as I just mentioned. But one thing it helps us do, it helps us to know, okay, for instance, if I understand that, green is normal, red is too much activity, and blue is not enough activity, then I know that if I see red, okay, these are the areas that I may want to look at more carefully when developing a protocol. So the quantitative metrics allow us to confirm what we see in the EEG and then develop protocols based on all that information and matching it to the person's experience or their endorsement of certain symptoms. The other thing that the quantitative metrics allow us to do is, for instance, if we look at a statistical map, and a statistical map would be one where we have where we compare an individual to a normative database, and that's where Z-scores come in, or Z-score neurofeedback, because again we're comparing the person's activity to a normative database. But again, that is not the only thing you should look at. If you're looking at brain maps, also look at the individual brain maps, because they give you a bunch of information about what's going on in the person's brain. And after a while, when I first started this, I relied more on Z-scores and Z-score type of information or statistical maps. But since then, I've learned to rely more and more on individual maps because they actually tell me more about the individual than a normative database. And usually I only use normative comparisons and head maps or different quantitative metrics when I have nothing to compare the individual to when I do my first assessment with that individual. But then as the next time or every other time, I just compare the person to themselves and their brain activity and how and if that matches the goal that the client is wanting to reach. And then I look at that activity specifically and I discuss that with the client. So there are sources out there that tell you, okay, there's certain biomarkers or patterns or signatures of certain disorders. Be very careful with that. Because, again, if I look at pictures like this, ADHD, depression, anxiety, and I look for these kind of patterns, this right here tells me nothing. These images tell me absolutely nothing. And why is that? So we know it's Z-scores because we have 0 to 3 and 0 to -3. So blue would be, compared to normative database, not enough activity, and red, too much. But too much of what? Here, it doesn't tell me whether it's in the alpha frequency, delta frequency, theta frequency, beta frequency. It doesn't tell me anything. It tells me there's a red spot in the front, and there's too much of something in the front. But that's it. So again, be very careful with this because we do not see these types of things in the brain. We see activity that corresponds or could correspond to certain symptoms. So keep that in mind. It is very important. So there are pros and cons to looking at quantitative EEG. The pros is, as I said, it's easier to visualize what's happening in a person's brain from a very broad perspective. The cons are that the QEEG does not include any kind of information about specific waves, such as morphology, which is important because certain types of morphology tell you what kind of activity is going on in the brain. There are normal variants. There are abnormal variants. There are, epileptiform type of activity and all sorts of other activity that you may not see if we just look at the quantitative metrics. So as this says, the QEEG lacks information, or the quantitative metrics lack information about the number of specific waves or even the morphology. And also, if they're infrequent bursts of a certain kind that may be very meaningful, they may be averaged out looking at a longer EEG record. So again, you may be missing data if you don't look at the raw EEG first. Do not take the shortcut and rely on automatization. Look at the EEG yourself. Don't be afraid of it, and learn to read the raw data. Here's an example of a NeuroGuide screen. And here on the sides, we have all sorts of different quantitative metrics that help us out in looking at the brain activity. For example, here, this FFT, the fast Fourier transform, tell us where or what the posterior dominant rhythm is. And again, that is very important because if we see a bifurcated or a bimodal type of posterior dominant rhythm, that may imply certain issues. Not necessarily, but it could imply certain issues. Then we also have Z-score compared to the normative database. We see how similar or how different this person's activity is to the normative database. Then we also have the head maps, as we've already talked about. And then we have connectivity maps as well. And again, those are different quantitative metrics that help us to picture the activity of the brain more easily. Then right here, the yellow brain with the red marks in it, that is an image or a Loretta image, which we're going to go over here in a second. So again, this is just an example of quantitative metrics that we can get with certain software applications. Various software applications use different types of imaging and different types of head maps and quantitative metrics, but all of them give you a certain common set of quantitative metrics, and those are the ones that are similar across different software applications. But also remember that most software applications, they use different algorithms in calculating the posterior dominant rhythm. So the best thing to do is to check what the posterior dominant rhythm is yourself and estimate that based on the raw signal, and then go to the FFT spectrum and verifying that. So again, for every raw data aspect that you see, you can always go to the quantitative metrics to confirm what your hypothesis is based on the raw data. Then we also can see that the EEG and the QEEG analysis, and they should match. So if you analyze the raw data, form your hypothesis, then you can go to the head maps, for instance, and verify if your hypothesis matches. If it doesn't match, you can go back and look at the raw data and you can decide why it doesn't match. And that is how you learn. And over time, again, you will understand what you should be seeing in the quantitative metrics based on what you see in the EEG data. Then, of course, there's Z-score Loretta neurofeedback, where we have, for instance, here we see certain activity that meets certain parameters in the brain. And then, again, we see down here how the person progresses in their learning. And again, if you look at this line, the percent reward scored, that should be going up and down, but the trend should be in an upward fashion. That tells us that the person's brain is learning to match the Z-score or the normative database activity. Z-score training has its place. Again, there are certain reasons for why we use Z-score training, specifically if we want to normalize the brain. If you work with elite performers, Z-score may not be the type of neurofeedback you want to use. You may want to just use amplitude training, because usually elite performers, in my experience, their brains look somewhat different from the people in normative databases. So I do not want to normalize the brain, because the thing that sets them apart, and the brain activity that sets them apart, may be the stuff that I'm training away. So I do not want to do that. So now we see these color-coded maps, head maps. And again, we have absolute power, relative power. And this, again, is from NeuroGuide. And amplitude asymmetry, coherence, phase lag. And again, we see here, if we see that the colors match a -3 to +3, that is normally what is depicted when we have Z-scores. And of course, up here we see Z-score FFT summary information. So again, this data is all good data. However, we have to make sure that it matches our EEG. So now that takes us to topographical mapping that uses the Loretta technology. These images, so these are not the person's actual brain. They are the person's activity superimposed on an MRI-like picture, so that it's more easier to understand where this activity is taking place. And Loretta uses an inverse algorithm to look at the source, or to look at the source of where certain activity is taking place. So if you think about where we have the sensors, we have them on the scalp. So there's nothing going into the brain that helps us localize where the activity is coming from. But again, we have a way of estimating through an algorithm that's an inverse algorithm, looking at the top of the scalp, and then these calculations estimate where the source is of certain activity. And why is that important? Well, it is important because if we want to know where the generator or the source of certain activity is, this allows us to know if is there one generator, is there 2 generators, 3 generators, For instance, if somebody had a TBI and they have the slow wave activity at a certain location when we do an EEG. So if we want to know, okay, where is the source of this activity coming from, then we could, because usually delta activity, we see that it localized at the brain, the surface of the brain. If there's certain shearing or cutting of certain axons of neurons in the white matter. So again, that will then show up on the surface as in the delta frequency activity, because that's usually the frequency that we see neurons firing at which are not connected effectively to a network. So that's when we see delta activity in an awake person. So again, that's why looking at Loretta maps is really important and has been a game changer, because now we don't just see what's going on at the surface, but we can estimate where this activity is coming from, and that helps us to even more fine-tune developing our protocols when it comes to creating those for a neurofeedback training protocol. Again, Loretta stands for low-resolution electromagnetic tomography, and again, we see here that we don't just look at the top, but we actually get like all the different axes, and up here on the image, you can see that it gives us the location, a 3D location of that activity. And for this individual, we see that there is more than one source of this activity. There's some here in the middle, there's some here in the back, and then when we look at it from the top, we see that there's some activity that is where the source is in the sides here in the back. So again, that's what Loretta images help us do. They help us to understand where the source is. Then there are some software applications that actually even tell you what the broadband area is of those dimensions. And then you can look at different websites such as fMRIconsulting.com, which then has an interactive atlas, and you can click on the broadband area that's indicated in your EEG report. And then you can look at what kind of activities that area of the brain is associated with, and then again you can match that to the person's symptoms. So then there are other types of software that are AI assisted. So again, those help us to further understand what kind of activity is going on. For example, we see that this particular software application from iSync Brain shows us here's the alpha frequency, and it is in the default mode network. So we see hyperconnectivity or hypoconnectivity between different areas of the brain. And you may think this is kind of hard to read, but what you need to do is you need to understand that, okay, this top here is the front of the head, this is the back of the head, and these are the sides of the head. So that makes it more easy to understand where the connection is going, where there's hypoconnection, hyperconnection in this frequency. And again, here are the different names of the different areas where the connectivity is or is not happening the way it's supposed to. So this is one way that this software application shows connectivity. Then this software application also shows a 3D image of absolute power maps, relative power maps, and again, the connectivity. And again, this is the right hemisphere looking at from the side. And again, this is an individual brain map where we see the person's electrical activity going on just based on looking at, for instance, a certain wave bin or frequency bin, such as it doesn't say here what frequency bin it is, but let's say this is also delta. Then this tells us that in this this individual's brain, there is not a lot of delta up here. Most of the delta is back here, and then where it's green, that is where compared to the rest of the brain, there's not an overabundance, or it's not the the place of highest activity or lowest activity, but it doesn't compare somebody to a normative database. So at this point, you can't say that this is normal compared to a normative database. This is an individual map, and it's just as helpful as looking at a normative database comparison, in my opinion, once you understand how to look at this. Then we can look at, this is another image of the connectivity in the delta frequency of various locations in the brain. And again, if this was the actual software applications, I could rotate this around and see if it's, where in the brain this activity or these connections are actually, or whether this brain is hyperconnected or hypoconnected. So that is it for this presentation. And I just want you all to also know that a successful practitioner and InMindOut are having a course series coming up in September. And here are the dates. We are having a biofeedback class, a neurofeedback class, a quantitative EEG, a didactic class. Then we also offer an advanced EEG interpretation class, which is awesome. Then also there's the 1 day of EEG mentor, QEEG mentoring, and it's a full day with an instructor or 2 instructors there. So again, in November, we have another series of classes. Also, we offer mentorship for biofeedback, neurofeedback, EEG. Just look us up online, and I'm thankful for you guys in participating in this webinar. And I hope that this was beneficial to you guys in understanding what EEG and QEEG really is. And again, this wasn't a webinar to explain fully every aspect of reading EEG and coming to a protocol and writing a report. But it is a start, and if you come to our classes, and then we can also get you to the point where you're able to do all this. And in our mentorship, we actually take a person from not being able to even know what an EEG looks like, or they see squiggly lines. But then at the end of the course with us and the end of the mentorship with us, they are able to understand how you get from looking at this raw data to writing a report. Now, they may not be completely proficient in doing it, but they are able to get through it with some help of the mentors. But then again, we also offer mentorship after those courses, and that is where, again, you will be fully able to do this this type of analysis of the EEG and QEEG, and you're able to write a report and feel comfortable and have a lot of fidelity in how you develop your protocols for neurofeedback, biofeedback, or for any type of treatment for that matter. So I want to thank you again for participating, and I hope you have a great evening.